Quantum mechanical treatment of one-dimensional harmonic oscillator. We know that in a simple harmonic oscillator, the oscillatory motions are taking place in one dimension or in one direction. Therefore, this simple harmonic oscillator is also called a linear harmonic oscillator or one-dimensional harmonic oscillator. It is useful for treating the vibrational modes of excitations, which are a common feature in many quantum as well as classical systems. These vibrational modes are the results of the displacement of the system from its equilibrium position. In quantum systems, these vibrational excitations are present in molecules, nuclei, solids, and molecular clusters. Usually, such vibrational excitations have the common feature that the energy spectrum has a unique signature whereby the spacing between the levels is quantized with an amount which is equal to h cross divided by omega, where h cross is equal to h by 2 pi. H is the Planck's constant. This harmonic oscillator model also serves as a prototype in the mathematical treatment of a large number of phenomena like elasticity, acoustics, AC circuits, molecular vibrations, electromagnetic field, and optical properties of matter. Let us move to the quantum mechanical derivation of the one-dimensional harmonic oscillator. According to classical mechanics, the kinetic energy of a one-dimensional harmonic oscillator is given by half mv square, and its potential energy is equal to, and it is represented by Vx in one direction, that is equal to half kx square. Therefore, classical mechanical expression for the total energy of the one-dimensional harmonic oscillator is given by E, that is equal to p square divided by 2m. That is, momentum is in the x direction, it is represented by px plus kx square by 2. Next, we have to convert this classical mechanical expression to corresponding quantum mechanical operator. It is a total energy expression, so the corresponding quantum mechanical operator is the total energy operator, that is called Hamiltonian operator, and the Hamiltonian operator corresponding to this classical expression for total energy is equal to h cap, that is equal to minus h cross square divided by 2m into dou square by dou x square plus k square by 2. Here the Hamiltonian h cap, that is time independent. Therefore, we can solve the time independent Schrodinger equation to find out its stationary states and the corresponding energy eigenvalues. The eigenvalue equation, that is given by minus h cross square divided by 2m into dou square by dou x square plus k square by 2 into psi x, that is equal to E into psi x. By examining this equation, one can see that this equation is similar to that of a particle in one-dimensional box with there is an additional time, that is equal to kx square by 2. This additional term makes this equation become very complex. So, on rearranging the equation, we can write minus h cross square divided by 2m into dou square psi x by dou x square, that is equal to kx square by 2 minus E into psi x. We know that 2 pi nu, that is equal to root of k by m. This is a general expression in classical physics. And squaring this 2 pi nu square, that is equal to k by m, or k is equal to m into 2 pi nu the whole square. Therefore, the above equation Schrodinger equation becomes minus h cross square by 2m into dou square by dou x square into psi x, that is equal to m into 2 pi nu square x square divided by 2 minus e into psi x, multiplying by 2m divided by h cross square throughout this equation. This equation becomes dou square psi x by dou x square, that is equal to 2 pi m v the whole square into h square divided by h cross square minus 2ma divided by h cross square into psi x, that is equal to 0. Let us substitute the constant term, that is 2 pi m nu divided by h cross, that is equal to alpha. Then substitute this alpha in the above equation. We can write dou square psi x divided by dou x square plus 2me divided by h cross square minus alpha square x square into psi x, that is equal to 0. This is a second order differential equations with the constant. The psi square is dou square by dou x square into psi x plus 2ma divided by h square minus alpha square x square psi x, that is equal to 0. Since we don't have the constant coefficient, we must using a power series method to solve this Schrodinger equation. So we use a power series method to find out the eigenvalue and the eigenfunctions of this second order homogeneous linear differential equation in the case of a one-dimensional harmonic oscillator. And the solution of the power series method has the form, if we assume that psi x in the x direction, psi nx, that is equal to e raised to minus alpha x square divided by 2 into f nx, where f nx is a function and it is in the form of a polynomial, or it is a polynomial function of degree n with the values of n being 0, 1, 2, 3, etc. This result, by substituting like this, or the presence of the polynomial wave function fnx makes the wave functions which is similar to that of standing waves in classically allowed regions and joining smoothly to falling of exponential shape in the classically forbidden region. So when the value of n is equal to 1, the wave function is psi x, that is equal to e raised to minus a square divided by 2 into f of x. Then differentiate this psi x with respect to x and again take the double differentiation of this wave function psi x. So we have to find out the values of dou psi x and dou square psi x by dou x square. The value of dou psi x by dou x, that is equal to e raised to minus alpha x square by 2 into dou psi x dou fx by dou x plus fx into e raised to minus alpha x square by 2 into minus alpha by 2 into 2x, or dou psi x by dou x, that is equal to e raised to minus alpha x square by 2 into dou fx by dou x minus e raised to minus alpha x square by 2 into alpha x into fx. On simplifying this, we can write dou psi x by dou x, that is equal to e raised to minus ax square by 2 into dou fx by dou x minus alpha x into fx. Similarly, find out the value of dou square psi x by dou x square, by differentiating the above equation once more. After a series of differential steps, we can write the value of dou square psi x by dou x square, that is equal to dou square fx by dou x square minus 2 alpha x into dou fx by dou x plus 2me divided by h cross square minus alpha into fx, that is equal to 0. This equation is known as Hermite differential equation, and this is a most common equation in mathematics, and the solution for the equations of this type, which is obtained by assuming that the function fx can be expanded as a power series. The solutions of Hermite differential equations are called Hermite polynomials. So, assume the fx can be expanded as a Taylor series around x is equal to 0. It is fx is equal to summation of n is equal to 0 to infinity cn x raised to n, or fx that is equal to c0 1 plus c1 x plus c2 x square plus c3 x cube plus etc. This is so. Next step, we are using a mathematical method by using the recursion relationship of the Cn form. We can solve this and substitute this value of fx in the Schrodinger wave equation. In order to solve this, first we write the dou fx by dou x and dou square fx by dou x square in terms of the power series. So we have to replace the value of fx, dou square fx by dou x square, and dou fx by dou x in terms of fx. So take the first derivative and second derivative of this Taylor expansion series in terms of dou fx and by dou x and dou square fx by dou x square. That is dou fx by dou x, that is equal to, take the first derivative of the fx expression, that we gives c1 plus c2 2x plus c3 3x square plus etc. That is equal to summation of n is equal to 1 to infinity cn into n x raised to n minus 1. Similarly, the dou square fx by dou x square, that is equal to c2 into 2 plus c3 into 6x plus etc., or that is equal to summation of n is equal to 2 to infinity cn n into n minus 1 into x raised to n minus 2. So then in the next step, convert this sum from 0 to infinity, because in the case of a harmonic oscillator, it can varies from the x can vary from, that is the displacement can vary from 0 to infinity, and let n is equal to k plus 2 and then the value of n is equal to 2 and k is equal to 0. By substituting this, we can write dou square fx by dou x square, that is equal to summation of k is equal to 0 to infinity c k plus 2 into k plus 1 into k plus 2 into x raised to k. Since n and k are dummy integers, we can write dou square fx by dou x square, that is equal to summation of n is equal to 0 to infinity c n plus 2 into n plus 1 into n plus 2 into x raised to n. Substituting these values in the equation, that is dou square fx by dou x square minus 2 alpha x into dou fx by dou x plus 2me divided by h cross square minus alpha into fx, and collect the terms of x raised to n. That is summation of n is equal to 0 on substitution. The summation of n is equal to 0 to infinity Cn plus 2 into n plus 1 n plus 2 x raised to n minus 2 alpha x into summation of n is equal to 0 n is equal to 1 to infinity Cn into n x raised to n minus 1 plus 2ma divided by h cross square minus alpha into summation of n is equal to 0 to infinity Cn x raised to n, that is equal to 0. On rearranging this, summation of Cn plus 2 into n plus 1 n plus 2 minus 2 alpha n Cn plus 2ma divided by h cross square minus alpha into Cn into x raised to n, that is equal to 0. Next step in this derivation is to set up of the recursor relationship. Now equating the coefficients of the general term x raised to n to 0. By equating this, we get a recursion relation which is common in mathematics. That is, the recursion relation for this one-dimensional harmonic oscillator, that is equal, after this substitution, is equal to C n plus 2 into n plus 1 n plus 2 minus 2 alpha n Cn plus 2ma divided by h cross square minus alpha into Cn, that is equal to 0. From that we can write the value of the coefficient Cn plus 2, that is equal to alpha plus 2 alpha n minus 2ma divided by h cross square divided by n plus 1 into n plus 2, the whole is multiplied by Cn. This is the recursion or recurrence relationship between the two coefficients for the Cn's. Let us define C0 and C1, that is equal to n. Then calculate all other values of Cn. If C0 is equal to 0, C1 is equal to 1, the power series is in the odd powers of x. If C0 is equal to 1 and C1 is equal to 0, we have the power series in even powers of x. So the most general solution is the combination series, and its solution is given for odd series and even series. For odd series, the solution is summation of n is equal to 1, 3, 5 etc. up to infinity Cn x raised to n as summation of n is equal to 0 to infinity, that is equal to Cn C2n plus 1 into x raised to 2n plus 1. For even value of n is equal to summation of n is equal to 2, 4, 6 up to infinity Cn x raised to n as summation of n is equal to 0 to infinity C2n x raised to 2n. Therefore, the power series equation, that is fx, that is equal to C01 plus C1 x plus C2 x square plus C3 x square, can be written as, or the solution of this power series equation can be written as fx, that is equal to summation of n is equal to 0 to infinity Cn x raised to n, that is equal to summation of n is equal to 0 to infinity Cn C2n plus 1 x raised to 2n plus 1 plus summation of n is equal to 0 to infinity C2n into x raised to 2n. That is, it is written as the summation sum of odd values of n and even values of n. Therefore, the wave function in one direction, that is psi x, and the value of n is equal to 1, that is psi x, that is equal to a into e raised to minus alpha x square by 2 into summation of n is equal to 0 to infinity C2n plus 1 into x raised to 2n plus 1 plus b into e raised to minus alpha x square by 2 into summation of n is equal to 0 to infinity C2n x raised to 2n. This equation is the general solution of a Hermite differential equation where a and b are two arbitrary constants. But there is a drawback. If the power series is infinitely long, that is, as x tends to infinity, the higher order terms of x in the function fx will dominate. So we have to consider these values. Then the wave function is unacceptable and become infinity as x tends to infinity. This difficulty can be overcome by using a truncation condition, that is, the series breakdown after a finite number of terms. If you truncate or reduce the series at some finite values of n, say v is the finite value, then psi would be finite at infinity, and we could be quadratically integrate that equation for both odd values of n and even values of n. So then the coefficient will become cv plus 2, cv plus 4, etc. is equal to 0 if alpha is equal alpha plus 2 alpha n minus 2me divided by h cross square is equal to 0 for b is equal to n. This truncation condition or this reducing condition leads to a quantum condition on energy, that is E is equal to h cross square divided by 2m into alpha into 1 plus 2v, since alpha is equal to 2 pi nu m divided by h cross square. This substitution we have done in the first stages of this derivation. Or the value of energy that is equal to h cross square pi nu into 1 plus 2v. On simplifying this, we can write the value of energy in the case of one-dimensional harmonic oscillator, that is equal to E is equal to V plus half h nu, where the value of V is equal to 0, 1, 2, 3, etc. So by requiring that the wave function psi to be finite as x tends to infinity, E become quantized. The general recursion relation can be therefore written by substituting this value of energy E, that is equal to h cross square by 2m into alpha into 1 plus 2v into the Cn2 equation. So the series is truncated or reduced by quantizing the energy. That depends on whether V is even or odd. Next, we have to find out the harmonic oscillator wave functions. The complete eigenfunctions of the harmonic oscillator can be expressed in terms of the Hermite polynomial, and the Hermite, this term is pronounced as Hermite of degree n, that is Hermite polynomial of degree n. And the wave function can be written as psi nx, that is equal to an into hn x e raised to minus alpha x square by 2, where an is the normalization constant for the nth eigenfunction and the hnx are the Hermite polynomials. The value of an can be calculated using the equation. It is a normalization constant, and the value of normalization constant, that is equal to an, that is equal to 1 by root of 2 raised to n factorial into root pi. The Hermite polynomial of degree n can be defined in the differential form by using Rodriguez type formula, and it can be written as hnx, that is equal to minus 1 raised to n e raised to x square into dou n by dou x raised to n into e raised to minus x square. By putting the values of n is equal to 0, 1, 2, 3 in the hnx equation, we get the Hermite polynomial of different orders. By substituting the value of n is equal to 0, we can write the value of h0 is x, that is equal to minus 1 raised to n, that is minus 1 raised to 0, or e raised to x square into dou 0 by dou x square into e raised to minus x square. that will become e raised to x square into e raised to minus x square, and the final value is equal to 1. Then if we put the value of n is equal to 1, h1x that is equal to minus 1 raised to 1 into e raised to x square into dou 1 by dou x raised to 1 into e raised to minus x square, that will become minus 1 into e raised to x square into minus 2x into e raised to minus 2x square. The net result is the h1x that is equal to 2x. Similarly, h2x that is equal to 4x square minus 2, and h3x that is equal to 8x cube minus 12x, and h4x that is equal to 16x raised to 4 minus 18x square minus 12x, etc. Next, we have to find out the energy levels of the harmonic oscillator. We know that the general expression for the energy for one-dimensional harmonic oscillator, that is equal to E that is equal to V plus half h nu, where V is equal to 0, 1, 2, 3, etc. If n is equal to 0, we get the first value E0 that is equal to half h nu. This means that the harmonic oscillator has 0 point energy and its value is equal to 1 by 2 h nu. That is, when V is equal to 0, the harmonic oscillator has a particular value of energy that is equal to half h nu. If n is equal to 1, we get the energy is E1 that is equal to 3 by 2 h nu. If n is equal to 2, the energy become E2 that is equal to 5 by 2 h nu, and n is equal to 3, E3 that is equal to 7 by 2 h nu. If we take the difference between the consecutive energy levels, that is E1 minus E0, E2 minus E1, and E3 minus E2, we get the value of the difference, so that is equal to h nu. Therefore, we can say that the energy levels of a one-dimensional harmonic oscillator are equally spaced or quantized with a value which is equal to h nu. Next, we have to interpret the wave function psi and its probability psi square in the case of a particle which exhibit one-dimensional harmonic oscillation. A plot of the wave function psi and its probability against x gives the following curve. Here, the first one represent the wave function plot, and the second one represent the general feature of the harmonic oscillatory motion, and the third one is the probability plot. From this, we can give some conclusions, or one can get some conclusions. The wave functions are either symmetric, even, whether it is even, or and antisymmetric with respect to x. The function psi square never negative and hence are necessarily symmetric. In the ground state V is equal to 0, there are no nodes, and on each successive state we have one additional nodes. The presence of nodes in these probability plots appears curious. That is, in that position the probability of finding the particle is 0. That is, there is 0 probability in the middle and finite probability on either side. The psi square plot also reveals the fact that the particle in the ground state has a maximum probability of being found at the central position, that is at x equal to 0, while in the excited state the probability increases towards the classical turning point. References: Quantum Chemistry P.K. Prasad and Chem Library text,